A rectangular wire loop with a resistance of 0.215. We'll use this, by the way. We'll just foreshadowing here, right? We're going to use the current is voltage divided by resistance, right? Because we've got the, right? And the voltage will be the EMF, right? Okay, it's pulled at a velocity of 11 meters per second, right? So we'll also use the fact that EMF is, what, BVL, okay? Induced current in a single strand of wire. Now, I'll show you why we can ignore other strands of wire, right? Okay. So the first question is, explain why there's an induced EMF in the coil. Explain when the EMF begins to be induced and exactly when it ends. Okay, so let's think about this, right? Our EMF is minus n d flux dt, right? Flux is BA cos theta, right? Well, theta here is 0, so this will be just 1. We don't have to worry about this, right? The area vector is pointing straight out of the page, and right, it's either 0 or -1, right? Okay, and then this magnetic field is either into the page or out of the page, right? So before we've entered the magnetic field, there's going to be no EMF in here because the flux isn't changing, right? We're just moving this thing around, but there's no magnetic field at all, so, right? But as soon as it starts to enter the field, as soon as it enters the field, if we draw a picture of it here, let's draw a picture. Ooh, that's a good picture. Oh, that's so good. As soon as it starts to enter the field, this magnetic field is taking up more and more of the area. So the area is changing, or the magnetic field is changing, however you want to think about it, right? Okay, so whilst it is entering the magnetic field, we've got an anti-clockwise EMF acting on this loop, and the current's going to flow, well, it's going to flow anti-clockwise, right? Okay, that means, by the way, it flows up the page, which will be important, inside the magnetic field, to the left, to the right, okay? All right. So it begins to be induced. Now, as soon as the thing is inside the magnetic field, like this, as soon as it's inside, there's no change in the magnetic field, no change in the area, right? So while it's entirely within the magnetic field, as long as it's totally uniform, right, then there's no change in flux, therefore no EMF. Now, by the way, what if it starts to exit the magnetic field? Doesn't ask that in this question, but as it starts to exit, right? Right, so here it would be 0, right? As it exits, we'd get a clockwise EMF, right? And then once it's entirely outside of the magnetic field, you'd again have 0, right? Because it's not changing, okay? So let's decide where it's going anti-clockwise as it enters the field, okay? So let's think about that. That anti-clockwise is a reaction to an increase in flux, right? And we're reacting to it by creating flux out of the page. Therefore, the change must be that the flux inside here is into the page. Okay, let's go through that reasoning again. Now, by the way, sometimes you can just guess. You can just say, okay, I'm gonna guess that the magnetic field is into the page, right? And then just see if it works. Does it make it go anti-clockwise? That's the way we're normally used to being asked the question, right? Okay, so let's look at this. I'm guessing it's into the page. Okay, so if we're increasing flux into the page, the reaction to that is to create flux out of the page. Anti-clockwise works. Okay, so therefore the magnetic field is into the page. We've answered that question. Okay. Then it says, B says, as the loop enters the magnetic field, there's a force opposing its motion. Explain the origin of this force. Well, it has to do with like Lenz's law, right? That if we're inducing an EMF, if we're getting energy in some other form, we've got to do work to get that energy, right? But let's look at the actual origin of this force is, let's look at this moment, right? Right here where it's entering the magnetic field, right? Okay, notice that there's a current flowing up the page. We're going to use forces ILB sine theta, right? In this case, theta is, what, 90 degrees or something like that, okay? And notice in this little segment right here, the current is flowing up, okay? So put your index finger up the page, right? Middle finger into the page, because that's the magnetic field. Do you get your thumb pointing to the left? Here's our magnetic force on this, right? Okay, do that again. So on this segment right here, the current is flowing up the page because it's going anti-clockwise in general on the loop. So put your index finger in that direction, right? Just like we did for this, right? Okay, index finger goes that way, right? B is into the page, right? That's your middle finger, right? And your thumb is going to point to the left, okay? So there's a force opposing its motion. It comes from this little segment of wire. Now, which way is the force on this? What about this little segment that's in the magnetic field? Well, try it. Index finger that way, middle finger to the page. There's going to be a force this way. But that force is canceled out by the force on this one, right? You can check that with your finger, right? That force would be up. So these little side segments don't do anything. It's this segment here that actually does something, right? All right. So we've explained the origin of that force. Okay. The EMF induced in the loop is 6.2 volts. Calculate the current that flows. Oh, we can do that. That's easy, right? So C, we're just going to say I is V divided by R, right? Okay, so that's going to be 6.2 divided by our resistance here. Okay, and you'll get quite a good current, right? Quite a large current. All right, so let's see. Calculate the current that flows. Calculate the force opposing the motion of the loop. That's interesting. How can we do that? Well, okay, so we've got the current. Ultimately, we need to figure out the force, right? But we need to figure out the magnetic field, right? So how do we do that? Okay, I've got an idea. I think what we need to do is we need to figure out what B is, right? What did B? B is something, right? Okay. I think we can use this, okay? So we can use that the EMF is BLV, right? Because we know that this is 6.2. We know that this is the 25 centimeters, okay? Because remember, it's the piece of wire that's moving across the magnetic field lines, like that. That's the one that's inducing the voltage, right? And then this velocity is 11 meters per second, right? So now you can find B. So now we've got B. We've got the current, right? So figure out the force opposing it, right? Force is ILB. Sine theta. Theta is 90 degrees, right? Okay, so the current is going to be the current you figured out in the first part, right? Okay, the L is going to be your 25 centimeters, right? Because remember, these forces cancel out, right? And then the B is going to be the B that you figure out, right? So calculate, and the magnetic field strength. Okay, so we've got that. We got the force opposing. All right. Okay, then it says show that the magnetic field is given by B equals the square root of RF over V over L, where R is the resistance of the loop, F is the force, V is the velocity, and L is the length of the side of entering the field. Okay, let's figure this out. Okay, so force is equal to ILB, right? Okay, is equal to, well, it's the EMF, right? The voltage divided by the resistance, LB, right? And then that is going to equal, remember the voltage is BLV, right? This is the EMF is this guy, BVL, right? BLV, whatever. Okay, divided by R. Okay. Times L B, right? Okay, and then that is equal to, well, we got to figure this out. We got to do a little figure in here, right? So now we're solving for B, right? Okay, so force, we've got force equals what, B squared L squared over R, oh, V over R. Okay, but we got to solve that for B, right? So we've got B squared equals RF over V, right? Divided by L squared. Is that right? Yeah. And then you're going to square root both sides, and I think you arrive at this, right? The squared goes away, you get a radical on the numerator. Okay, just be prepared to do stuff with these, right? Okay, key equations, we've got this guy, right? I'm going to ask you to derive some other expression, right? We've got F is ILB, right? It's crazy. It's a crazy expression. All right.